Hello. Today we are starting the new chapter, that is the collisions. In this chapter, we will discuss some key topics like impulse, momentum, conservation law of momentum, collisions, in which we will discuss the elastic and the inelastic collisions, coefficient of restitution, and the center of mass. So we start this chapter with the topic impulse and momentum. Suppose particle has the mass m and its velocity is v1 at the time instant t equal to t1, and it is under uniform accelerated motion. Uniform accelerated motion means A is constant, acceleration is constant. So due to this acceleration, its velocity increases and time instant t equal to t2, suppose its velocity becomes v2. For uniform accelerated motion, we can use the equation of motion. One of the equation of motion is v equal to u plus at, where v is the final speed at time t, u is the initial speed at time t equal to 0, and a is the acceleration. Substituting the values in this equation, we will get v2, this is the final speed, this is at the time t2, it is equal to v1, this is the initial speed, plus a is the acceleration, and time interval, this is the time interval in which body is accelerated. So time interval will be here t2 minus t1. So we can put here t2 minus t1. We multiply this equation by the mass of the particle. On multiplying, we will get mv2 equal to mv1 plus ma t2 minus t1. We can write it as also mv2 minus mv1. This mv1 is taken left side, and remaining is ma t2 minus t1. This m is the mass of the body and a is the acceleration in the body, and this acceleration is due to a force, and force by Newton's law is ma. So we can write this as mv2 minus mv1 equal to f into t2 minus t1. Now we analyze this equation. Here, this right hand side is the product of force and time interval for which force was acting on the particle, and this is called the impulse. Impulse is the product of the force and the time duration for which this force is acting on the body. We represent this impulse as j. This is a vector quantity, so we can write impulse j equal to f into t. We write it t2 minus t1, or simply duration we can represent it as f into t, where t equal to t2 minus t1. So this is the impulse of the force which acts on the body for a time interval t2 minus t1. If we check, it is a vector quantity. Its unit is Newton second. Unit of force is Newton, and this is the time interval, time is second. So it is Newton second. If we write its dimension, so dimensions will be, dimension of Newton is ml t minus 2, and second is time, so dimensions will be ml t minus 1. So this is about the impulse. Now we check the left hand side. This is the difference of the two similar type quantities. First is the mass and the velocity after the time, at the time instant t2, and mv1 is the product of mass and velocity at the time instant t1. So we can write from this equation that mv is a quantity that is called p, we say this as momentum. So momentum is the product of mass and velocity of the particle at any instant. In vector form, we can write it as mv. M is a scalar quantity, v is the velocity, this is the vector quantity. So momentum is also a vector quantity. We say this momentum as also linear momentum to differentiate it from the angular momentum, which we will discuss in the rotational motion. This is a vector quantity. Its unit is, if we check the formula, it is the mass, that is the kilogram, and v is the velocity, that is meter per second, and it is equivalent to Newton second. Its dimensional formula is also ml t minus 1. So we can say here that change in momentum, delta p is the change in momentum. Change in momentum is p2 minus p1. p2 is mv2 and p1 is mv1. p2 is momentum at time instant t2 and p1 is the momentum at time instant t2. So change in momentum is equal to the force into t2 minus t1, that is the impulse. So from this equation it can be written as change in momentum is equal to the impulse of force. And in vector form we can write it as, in vector form it can be written as delta p, this is the vector, that is equal to p2 minus p1 and it is equal to f, this is the vector, into t2 minus t1. Now we take the conservation law of linear momentum. Previously we have defined that momentum is, and it is the linear momentum. Momentum is p equal to mass into velocity, and direction of momentum is same as the direction of velocity. If we differentiate momentum with respect to time, then we will have dp by dt equal to a differential of mv. We take the mass as constant here. Maybe mass changes. In that case, we have to differentiate mass also. But for our particular case, we are considering mass is constant. Then we take it out of the differential and it is dv by dt. And rate of change of velocity is acceleration. And product of mass into acceleration is the force, and this is the external applied force. So we can say from here that rate of change of momentum is the applied force. We can conclude that rate of change of momentum, that is a linear momentum, will equal to the applied force on the particle or the system. Now, if F external is 0, that means there is no applied force. In that case, this dp by dt will be 0, and differential of a function will be 0. It means that function is a constant term. So momentum is constant. So we can say if external applied force is 0, then momentum is constant. And this is the conservation law of linear momentum. It says that if there is no external force applied on the particle or the system, then its linear momentum will remains conserved. And it is a universal law of conservation of momentum. That means it is applicable in each and every situation. Here we make some notes. When we say P total, it is the sum of the momentum of individual particles. Suppose system has n particles, then total momentum of the system will be sum of all individual n momentums. That gives the total momentum of the system. If there is no external force applied on the system, that is F external is 0, then this implies that P total of the system will be constant. And this is constant in terms of magnitude and direction. Third, when two bodies interact with each other, then their momenta, that is sum, will be constant or conserved. Fourth is, it holds whatever the nature of internal forces, conservative or not. This is in contrast of mechanical energy. Mechanical energy is conserved for only internal forces which are conservative. For non-conservative forces, mechanical energy is not conserved, although total energy of the system will remain still conserved.